Awesome. Welcome to the talk, LLMs on Kubernetes squeeze 5x GPU efficiency with cache, route, and repeat. I know it's probably the last talk of the day. Thanks. I'm really grateful to everyone who showed up here. All right, cool. Let's start. I'm Suraj. I work as a principal software engineer at Microsoft. Yeah.
Hi, everyone. I'm Yuhan. I'm a fifth-year PhD student at the University of Chicago, working on systems for machine learning.
All right. Cool. Before we talk about any efficiency or anything like that, let's first get some basics clear, right? So what's inference? The diagram that you see, it's just a placeholder, I would say. Like you'd see there's a client, a pod running on node, and that pod is occupying all the GPUs. There is a sample request going back and forth. So OK, so what's inference, right? Inference is just a forward pass of the model. So there are no gradient updates, just the prediction. And it's like running any other microservice on Kubernetes, right? Instead of just handling API requests, what it's doing is it's generating text token at a time. And as each request grows, as in when the output grows sequentially, the latency also accumulates, and then that's the whole generation process. And since each request is long running, it's behind the scene. It's also consuming the GPU memory. That's why all the GPU efficiency matters. And the analogy that I like to give is think of model training like building Docker images and serving using those Docker images on Kubernetes. So and before we understand how to gain the efficiency, let's see what metrics we are trying to optimize. One is the throughput. Throughput is token per second of whatever the deployment system looks like. So we are trying to maximize that. And the other is time to first token. We are trying to minimize time to first token. So if you ask what time to first token is, you know how you write a prompt in ChatGPT, and then you wait for some time before the first word shows up? So that time between sending that request and waiting for the first word, that's the time to first token. We'll see more. There have been a lot of talks that have gone into the depths of each of what these metrics are. I have a slide at the end that you can take a picture later, look at the recordings if you have not attended those. All right, cool. So what are the various serving engines out there? So vLLM by far is the most popular one. All the open source models that come out, they come out with support of vLLM out of the box. So people because this is the inference engine that since it supports everyone gives it a try. The other one is SGLang, and then there is one from NVIDIA, TensorRT. This is by no means an exhaustive list. I am pretty sure there are more, but I think these are more popular in the cloud-native ecosystem. So, OK, before let's look at from a client point of view, what really is happening when you send a request to an inference engine. So what you usually have is a chat window. You type a prompt. But behind the scene, what's going on is a JSON like this is sent to the inference engine. So this is a lot of details have been removed from this, but I'm just giving you what you have typed and what shows up in the JSON. You get some response, and then you send another request. But when you type another prompt, everything in that context is sent again to the inference engine. So you can see how every time the chat increases, this JSON is growing more and more. So keep this in mind, because this is one of the crux of how we do optimization. OK, and you get some response that's just placeholder, just to show you that it works. OK. OK, so what happens from the server side of the picture, right? So there is GPU memory involved, of course. And right off the bat, when you start any inference engine, it first downloads the model weights, loads into the GPU memory. So that's non-negotiable. You cannot get around this. Like, you have to load the entire thing into GPU memory. It has to stay there. It's always resident. And then the inference engine also configures some space for storing its KV cache. And this grows dynamically as more requests will come in, but it already like assigns certain amount of space. So, and then there is some space left for like other types of overhead, system overhead. So you can see like this is, and these numbers are by no means representative of anything. It's just to show you that you can see like a ballpark assignment of GPU memory like this. So let's see like a query, like what happens like in a query's lifetime, right? So like when you send that prompt, like all those tokens are loaded at once, and while the inference engine is processing those tokens, it is generating something called as KV cache. We'll look a bit deeper later what KV cache is, but understand it's some metadata that is generated that is then used for the decode phase. So until that decode phase starts, and from the time you send that request, that's the whole time to first token that I mentioned earlier. So decode starts like one token at a time, and it's using that KV cache that was generated during the prefill phase, right? So that's a single query in action. And to give you some high-level overview of KV cache, I mean, I'm pretty sure this is not exactly accurate, but you can think of each word like a token here. Again, that's also not accurate. Each word could be a token or could not be. It depends on the tokenizer of the model. But think of each word as, in this example, as one token. And with each word, there is associated key and value metrics behind the scene, and that's generated per transformer layer. So this is being generated in the prefill phase, and the decode phase then uses this, right? So this is going to be one of the main topics of how we optimize our inference. So the challenges of vanilla approach, right? Like whatever we saw so far, that's vanilla. There are no optimizations here. So all of this is fine when there are few requests, but as concurrent requests show up, and long prompts show up, like we saw before, the prompt gets, it grows quickly. The GPU KV cache also starts to fill up. So when that happens, the inference engine has to decide, okay, like what KV caches are not relevant for this particular request I'm serving. It will remove all those KV caches that are not relevant. So, and if the same request comes again, then it has to process the entire request that you sent. It has to generate that KV cache again. That work continues. So the downside is the time to first token increases, and GPU is redoing the same work that it has already done. So this inefficiency, like it compounds really fast. So so how do we reduce this extra work, right? One of the ways is like you can move that KV cache somewhere, or load that KV cache from somewhere. You can, do both. So you can use like tiered storage, right? Like GPU being the fastest, its memory, and then CPU memory, and then a disk or a remote storage. So the idea is that use GPUs for active generation and not as a storage, like use something else for storage. And this point I wanted to make, like in computer science, we keep seeing these problems, right? Like caching is nothing new. We just revisit it, resolve it at a different layer. We have been doing this for a while now. So similarly, we'll be seeing how to do KV cache offloading. So the idea is instead of recomputing, do the reuse. So how do you do it for in the context of LLM inference? So that's where LMCache comes in. Like I said, there have been other talks that have gone into the depths of LMCache as well. I'll like show you at the end. So very quickly, what is LMCache? It's a open source project. It acts as the caching layer that sits between the inference engine and various storage, including GPU, if we like GPU's high bandwidth memory. So it extracts those KV caches that are normally in the GPU memory and then stores it to wherever you have configured it to. It could be CPU memory, remote, like local NVMe disks, or remote storage. So, and it has this tiers where like all the warm caches or the hot caches will be always kept in the GPU memory. The warm ones could be configured to skip in CPU, and then remote ones. And today it works with vLLM and SGLang, like you can use with both inference engines. And so the whole idea is that since you are not recomputing it, you're bringing it from somewhere, all the redundant requests don't happen, hence the prefill becomes really small, as in like time to first token becomes really small, and then that's why you get higher throughput. We'll see those results, benchmark results as well. To give you like a higher level overview, like this could be a mental model you can think of, where there is inference engine like vLLM or SGLang, and at the bottom there are various storage tiers. And LMCache cache sits in between, like it's transparently doing loading, offloading those caches to other memory, and then loading it back in when they're needed. So for further talk or further benchmarks and other stuff, I'll let Yuhan take over.
Okay, thanks, Suraj, for giving the high-level overview of what LMCache is. So now I'll talk about some real benchmarking results that shows how LMCache can improve the performance of LLM inference. So here for the setup, we use emulated multi-round QA question answering. And so it has like 40 concurrent users, and each user asks questions for multiple rounds based on a 10K long input context. And for the models, we use the minimum number of GPUs that can host the model weights. And here we show a bunch of results on Llama 3.1 8B, Llama 3.1 70B, and Qwen 32B. And so here we enabled LMCache CPU offloading feature, where KV cache will be offloaded to CPU memory whenever it does not feed in GPU memory. And so here, let's look at the results on Llama 3.1 8B instruct. And here in this figure, the x-axis is the QPS, which is basically the arrival rate of the request. And y-axis is the time to first token, which includes the time to prefill the new query and the time to load KV cache from CPU memory back to GPU memory. So here, this is where the latest vLLM is at. And this one is by default enables vLLM's GPU prefill caching. And this is vLLM native CPU offloading. And this is where LMCache is at. So here we can see that at the same level of TTFT, LMCache can improve the throughput by more than 2x. And on this figure, I'll show QPS versus ITL, which is basically the time between each consecutive output tokens. So this basically measures latency for each decoding step. And in this figure, this is vLLM, this is vLLM's native CPU offloading, and this is LMCache. And as we can see here, LMCache can both improve TTFT and ITL. So here I'll show results on a larger model, on Llama 3.1 70B. And in this figure, this is vLLM's CPU offloading, and LMCache. So here we can see at the same level of TTFT, LMCache greatly improves the throughput by 5x. And similarly here, in terms of ITL, this is vLLM's CPU offloading and LMCache. And under this scenario, on this larger model, LMCache can also greatly improve the performance. So I'll show the results on another type of model, which is the Qwen 32 billion model. And on this figure, as for TTFT, this is vLLM, CPU offloading, and LMCache. Here at the same level of TTFT, we improve the throughput by 3x. And similarly, in terms of ITL, this is vLLM offload, CPU offloading, and LMCache. So just to summarize, LMCache can greatly improve the performance of LLM inference across these different sizes of model and different types of models. Okay, so by far we have seen like how LMCache can improve the performance for a single instance of LLM inference. So what if we have a distributed inference setting? And by that I mean like if we have multiple replicas serving the same model. So the key question here is how to determine the right replica to send the query to. And by that, I mean, for example, we have a user which sends requests to, say, like there are 3 replicas serving, say, Llama 3.1 AB. So we need to determine which replica to choose for this type of request. And to determine this, we need a request router that it can ideally it can smartly determine where the request should be routed to among all these replicas for the model. And since we have LMCache, we can store KV cache in, like say, the local memory of each replica. So here it adds another level of consideration in this router. So with that, I want to briefly introduce KV cache aware routing. And for KV cache aware routing, for example, the user first sends request number 1, and the router randomly picks a replica to send the request to. And for example, it sends request to replica 1. And then on replica 1, the LLM generates a KV cache of it, and it stores to the local memory managed by LMCache on this replica 1. And next time for request number 2, it has a prefix match with request number 1. And so now what should we do? So this router here for KV cache over routing will see like which replica has the information, has the cached KV. And with this, you need to enable, will enable the KV cache manager written in LMCache. And basically, this manager keeps the information of which location the LMCache, the KV cache sits in. And then the KV cache manager of LMCache told the router that it's, the KV cache is in replica 1. So the router sent the request to replica 1. And then the KV cache will be loaded from the local memory to the GPU memory of replica 1. So with this, the TTFT can be largely reduced because we can reuse the repeated computation that happened before on this replica. So this features, this KV-aware router is enabled in another of our open source project called vLLM Production Stack. And so vLLM Production Stack, it's an open source project for Kubernetes native vLLM deployment. And so it has all the features such as smart routing logic and auto-scaling based on LLM specific metrics such as load and KV awareness. Yeah, so with that, I want to show a demo for KV-aware router. Okay, so wait. So how can I see it?
Maybe you'll have to like look back and control it.
Okay. Okay, so in this demo, I'll show KV-aware routing. So first, you need the Helm chart value to specify the deployment. And here we are using GPTOS as 20B. And we deploy it on 4 replicas. And here in the router spec, you need to specify KV-aware as the routing logic. And then you can do Helm install to start the deployment. And you can also use control get pods to monitor the status of the pods. So here I'm accelerating it, but now you can see that the pods are ready. Okay. And we can monitor the logs, the live logs of the router pod. Okay, now we do a pull forward to enable a request to be sent to the router. And now we send a request to the router asking, like, what's the capital of France? So here in the log, you can see that there are lookup message to query the LMCache KV Cache manager to see if the KV Cache for the input prompt has been stored in any of the instances before. And since this is a new deployment, there hasn't been any instance processed the KV Cache before. The return message is empty. So next, let's send this request again, the exact same request. Oh, by the way, the request is routed to this IP address. Okay, so then we send the request again. And what we can see here, it's performing the KV Cache lookup. And here in the return message, we can see that the KV Cache manager returns the instance name that has a KV Cache for the input prompt. So this is the instance name, and it also returns like the storage device that stores the KV Cache for the input prompt. And it returns the number of KV Cache, the match tokens in the backend. So now the router, based on this information, routes a request to the exact same IP address as the first request. Okay, so with that, that's all about the demo. And yeah, I think it's right here. Okay, and you know how Suraj shows like the prefill and decode phases can happen in one pod. Now I'll briefly talk about prefill decode disaggregation, which is like you can separate these 2 phases on different GPUs, and this has been proven to improve the efficiency of our inference as well. So with that, so if the user sends a request to the router, and the router will send a message to tell the prefiller engine to start the prefilling phase. And then the prefill engine will generate the KV cache and send the KV cache to the decoder engine. Then the prefiller engine will tell the router that the KV cache is sent, and after that, the router will send a message to the decoder engine to let it start decoding. So on the decoder engine, it will use the KV cache generated and transferred from the prefiller engine to do decoding. So this PD disaggregation allows prefill and decode phases to be scaled separately, and this can achieve a much lower SL violation rate. So by that, I'll show a demo for PD disaggregation as well. Okay. So this demo is also recorded with vLLM production stack. And to start the deployment, you also need this Helm chart values. And we can do Helm upgrade or Helm install to start the deployment. And we can monitor the status of the pods. And here we have 3 pods, one for the router, one for the decoder instance, and one for the prefiller instance. So let's take a look at the Helm chart value file to see the configs. So basically, we'll need separate configurations for prefiller and decoder instances. And for example, for this prefill called llama prefill, like the most important thing is like in the LMCache config in the llama prefill pod, you will need to specify the KV role to be KV producer. And what this means is that it's a prefill engine, and it will generate the KV cache and transmit the KV cache to the decode engine. So we use Nixo to do this KV transfer, and this PD llama decode engine service, this specifies the destination of the KV transfer, which is the decoder engine. And for the llama decode pod, we also similarly, we need to specify the LMCache config. We need to specify the role of the engine, which is a KV consumer. And this means that it will take in the KV cache transferred from the prefiller instance and do the decoding. So, and it also has a config for Nixo. And in the router config, the router spec, you need to specify disaggregate prefill as the routing logic. Okay, we can use kubecontrol-get pods to see the status. And we can also get services to see the started services. And this is needed for both prefill and decode, because the prefiller engine needs to transfer the KV cache to the decoder engine via this service name. Okay, and we can also check the log. This is a decoder log. And this is the prefiller engine's log. So we can see that the pod has been started and it's ready to take request. Okay, so you can see that they are all ready. And in the router pod, you can see the log that it discovered new serving engine pods called llama prefill and llama decode. And we do a pull forward to send request to it. Now we send a request to this router pod. So you can see that in the router, it shows like the time at the prefiller engine side. And in the prefill pod, we have the log that it shows like it stores the KV cache for all the tokens in the LMCache backend, and it uses Nixo to transfer the KV cache, and you can also see the latency for that. And let's take a quick look at what decode pod looks like. So here you can see that it retrieves the 10 tokens KV cache from the LMCache backend, and it's sent from the prefiller engine. Okay, and back to the request. So you can see that the request it's successfully finished. Yeah, and so this is a demo for the PD disaggregation in production stack.
Yeah.
Yeah.
That's sorry, go ahead. No, I was going to say the first talk talks about LMCache in depth, so you should check that out. The second one talks about how inference gateway can be used to do prefix matching. And the third and fourth goes into the benchmarks of it. So yeah, that's our talk. Thank you for coming. If you have questions, I guess we'll be here. Yeah. Thank you.
Thank you. Yeah, good question. So the question.
Can you repeat the question?
Yeah, the question is how does LMCache improve if we apply LMCache on other types of inference engines? So the answer is we actually have some benchmark results on LMCache integration in SGLand, and it's in our technical report. I can share the paper with you. So on that results, we have found similar improvements in terms of the inference throughput. So yeah, does that answer your question?
So based on your experimentation, which inference engine is the best for performance-wise?
You mean comparing the inference engine itself's performance?
Correct. All of them using the LM caches. I'm just curious which one is the best.
So it's a question comparing the two inference engines, the many inference engines itself's performance, or asking, are you asking how which one LMCache has the best performance?
Which one has the best performance?
For LMCache?
Yes.
Okay, so I would say for vLLM, we have the best performance, and but for SGLand, we also have performance gain compared to its vanilla SGLand. And we are on par with SGLand's native CPU offloading. Yeah. Okay, thanks for the question. So if there are more questions, we can talk offline. Yeah, thanks everyone for coming to the talk.